Okay, chromatic number of a graph. Chroma means color, right? So it's about being able to color a graph. Now, I've already spoken a little bit about color, so we're talking about bipartite graphs, right? So bipartite graphs are some graphs such that you have two different groups, and any edge, so two different groups of vertices, so that any edge that lives in this graph is connecting different groups, and you never connect between the two. So this is not permitted, but this is okay. This is okay. That's okay. Yeah, so this will be a yeah. So this will be an example of a bipartite graph, and the criteria for figuring out if the graph is a bipartite or not is if there's a way to color these vertices in two colors. So, by the way, I forgot to say that what the rule is. So, rule for coloring is that any two vertices joined by an edge must have different colors. So in other words, if two vertices are joined by edge, they're called adjacent. And what I'm trying to say is that all adjacent vertices must be of different color. That's the idea, okay? So if you have a bipartite graph, of course, you can take one group and color it red, and take the other group and color it blue. Now you have a coloring of this graph following this rule, right? So anything that's joined by an edge, well, we know by the definition of what bipartite means that edges only exist if they are between two different groups. So one and the other must always be in different colors, right? Does that make sense? So, so the theorem that we went over is that a graph G is bipartite if and only if the chromatic number of G is equal to 2. Okay. And I keep saying things before defining, I'm sorry. So chromatic number of a graph G is the minimum number of colors required to obey the above rule, the coloring rule. Okay. Of course, you can use more colors if you want, right? You can make this as green, and it will still obey the rule for coloring, right? But if you want to have minimum possible coloring, then 2 is the lowest you can go. Okay? Now, if you go with just one color, then it's impossible because every one of these will be the same color, and there's no way to connect two things without violating this rule, right? So that's kind of G. Now, can you think of a graph that would require 3 colors? The simplest one? Well, 3 colors, you need 3 vertices, right? So what kind of graph with 3 vertices require 3 colors? Okay, let me ask this. If you just have this, how many colors do you need?
2.
2. You can put this as red, right? And the 2 other ones is blue, right? Okay. But then the moment you connect these 2, what happens? Then these are same color, so that's going to violate this rule. So that means this now has to have a different color, right? So you have 3 different colors. You need at least 3 different colors for this to work. Okay? Now, this graph is known as K3 because you have 3 vertices and you put edges to every pair that you see. That's called K3, right? So let's think about K4. K4 is you have 4 vertices, and then you connect between every possible ones, right? So let's do this, do that. Okay. A lot of times people just connect it like this, but then it's no longer planar, so I just wanted to draw something that's planar. Okay, how many colors do you think you need? So let's say we start with the red here. Okay, now that means this has to be different from here, this has to be different from here, right? Now the question is, can these 2 be equal color? Is it okay to have these 2 colors, two vertices to have the same colors? No. No, because they're connected by this edge, right? So that means I need one of them to be blue and the other one to be light blue. Something like this. They have to be different colors, okay? Because they're connected. But wait, there's this 4th point. What about this? This has to be different from every one of these, right? Because this is connected to every one of those. So, I mean, I don't have any more colors, so let's just call that black, okay? So we are forced to have at least how many colors? 4, right? So what we just observed is the following. The chromatic number of K3 is 3, okay? And the chromatic number of K4 is 4. Okay, what do you think about K5? Now K5 is the first complete graph that's not planar, so you need to draw it so that the edges overlap. So you have this and then. Okay. So these are not vertices. You just have 5 vertices. Okay, what's the chromatic number for K5? I'll give you a moment to think.
Is it just 5?
It's still 5, right? Yeah, it's just 5 because everything is connected to the other. So all of those have to have different colors. So when you have a complete graph, then they have to be different from another, right? So you need yeah. So the result I'm trying to explain is the chromatic number of Kn would always be n. which is not so hard to see. Just for completeness, let me talk about K2. K2 just has two vertices, and there's only one edge you can draw, so that's K2. K2 will have chromatic number 2, this will be 3, 4, and 5. Okay? Now, in fact, there's a concept of a clique. So, a clique, the definition, a clique is an induced subgraph that is isomorphic to Kn. So if you have, for example, let's say you have a graph like this, A, B, C, D, E, then an induced subgraph is like you choose some of the vertices, and every edge from the previous graph that uses these vertices are taken from it. So if you just take the induced subgraph of ABC, that forms a clique, right? Is a clique. And then you can also have C and D, right? That's also another clique, right? Because that's K2, right? This is isomorphic to K3. This is K2. They're all from here, right? These are both induced subgraphs from here. Is that okay? All right. And then there's a name. There's a number called omega n. Oh, sorry, omega of g. Sorry, omega of g, which is this max size of clique. Okay, so here, for this graph, if I call this graph as G, then omega G is 3 because I see that this is the maximum graph, maximum induced subgraph that's isomorphic to one of the K's, right? This is K3, so this is 3. And K4 would be this guy, and I don't see anything like that in here. So the maximum you can come up with is 3, right? Now, because we know that the chromatic number for K3 is 3, we have a simple observation that the chromatic number must be equal or more than this number from the clique. Right, so there's no way to color this with less than three colors because of the presence of a K3 in this graph. Okay? Now let's see if that's enough. I think it's enough, right? So if I start with red here, then I need these to be different colors. Okay, so blue, light blue, red, and then these just have to be different from this one, so I can just put red for those. So indeed, I have chi of g equals to omega of g for this case, okay? And there's a name for that because a lot of cases do have that equality. So we say if the chromatic number and the omega of g is equal, we say g is perfect. Perfect graph. Now, if you just look at that example only, you might think, shouldn't that be equal all the time? But the answer is no. So here's a simple example. Think of this case when you have 5 graphs. So there's a graph that is not perfect. Okay. This is called a cycle or cyclic graph. Cyclic graph. So if you have a cyclic graph of order 5, if you have 5 of them, then you can start out by putting one of the colors on one side, and then because the next color has to be different, let's choose 2 of them both as red because we want to save our colors. Okay? So try to use the minimum number of colors. But then in the next one, you have to be different from the previous red. So we can go back to the light blue. But if you put light blue on both of them, then they have the same color that's neighboring, right? So you're forced to have one of them as a third color. So here we see that the chromatic number of this graph is what? Chromatic number of this graph is what's the chromatic number of this graph? 3. Now, what about the maximal click? Well, I don't see any K3 here, right? In this graph, I don't see a K3 there, right? So the maximal thing that you can see is something like this. So this is a click, that's a click. So omega of G, at most you see just K2, which is 2. So as you can see, in this case, you have bigger chromatic number than the maximum size of the click. Okay?
How come it can't be like 3?
Huh?
How come W the
I mean, to have WG as 3, then you need K3, right?
yeah.
Do you see such a thing? I mean, if there was like a this, then suddenly then it's W of G will be 3. But none of that exists, right?
Yeah.
Yeah. So W of G is 2. Yet the minimum coloring that you can have is 3. Okay? All right. But there's a class of planar graphs that are quite important here. So there's something called wheel graphs. So for example, W5 is like 5 vertices, but one of them is in the center. But the other one's like that, okay? And it's a planar graph. So put it like this. So there's a central hub, and all the other vertices are connected by the outer edge, but then all the vertices are connected to the center. Okay? Just like this. Okay. So question is, what is the chromatic number for W5? Okay, and now let's think about W6, which is you have a center point and 5 vertices. This is W5. Okay, no, W6. W6. Okay, so figure out the chromatic number for each one of these. Same? Okay, great. Yeah, that's right. So this will be 3 and that will be 4. Because first of all, the outer edges, you can just color it with 2 colors. So one observation is that if you have a cyclic graph like this one, then the even ones can be colored with just 2. If you have odd ones, you need 3 colors, because if you alternate at some point, the last one, you don't have a right color to color. So if it's odd, it's always 3. If number of vertices if you have a circular graph, and if the number of vertices are even, then it's just 2. If it's odd, it's 3. Okay? So here I know that you can just color this with 3, but then this hub has to be different from every color here. So you can't use any of these colors, therefore you need another color, and therefore that gives you 3 colors. Okay? Same thing here. Because we know that the coloring for the outside is 3, the center one has to be a different color than the 3 colors there, so you end up with 4 colors. Right? Okay. Now let's think about the clique number, omega of g of this thing. What's the clique number for this one?
3.
Yeah, this is 3, right? You have a subgraph that's like this. I mean, K4 is this guy. So you might think, isn't this here? Well, not quite, because there's a vertex here. So the thing is, if you take these 4, only the outside ones, and look at the induced subgraph of this, these edges exist here, but these 2 edges don't exist here, right? So the induced subgraph by taking these 4 is just this, not this one. So it doesn't have K4, therefore this has clique number 3, okay? And in this case they're equal, so it's perfect, okay? Here, again for the same reason, omega of g is 3, right? It doesn't have this guy here. But in this case, this is bigger than this one, so it's not a perfect graph. Okay? All right. Now, for planar graphs, here's a question. So 4 colored here. Now we have examples of graphs that require 5 colors, which is K5, right? And Kn requires n different colors, so there is no minimum number of colors that work for everything. But then at some point, a long time ago, when color printing was expensive, the printing presses, they wanted to reduce the number of colors to draw things. And one of the problems they had was when you have maps of different countries. So let's say you have this one country, there's another country, there's another country, there's another country, just like that, right? And then the question is, how many colors do you need in order to paint this as a map so that any two neighboring countries have different color? That was an actually important question back then when printing presses required different colors. And maybe nowadays it's still an important problem for some cases, okay? And this one doesn't look like a graph, but you can think of this as a graph by doing the following. Put vertices for every point. Every country put vertices, okay? And if two countries are neighboring, you connect them by an edge, okay? Connect them by an edge, connect them by an edge, connect them by an edge. These two are neighboring, so connect them. You do that, okay? Now, there could be some weird cases when you have a multi-connected case, so that if you have a small country between two large countries, then you might have this connection and that connection and this one like that, okay, so that you have three vertices, but there are two edges connecting these two vertices. So this is a multi-graph, not a simple graph, okay? But as long as these two are different colors, the rule for coloring is not really affected by whether you have a simple graph or multi-graph, because if it's connected in two cases, as long as they're different, that's still okay, right? Yeah. So we don't really have to worry about the resulting graph to be a multi-graph. All you have to know is that if you have a map and come up with the graph by putting dots for each country and then connect by edges if the two countries are neighboring, then you have something like this. Oh, there's something that we recognize. What is that? This W6, right? Yeah. You have 6 countries like that. Okay. So how many colors do you need? 4 colors, right? Yeah. So in every configuration that printing presses try to do, they always found that 4 color was enough. They can always color countries in 4 different colors, and they were able to do this. So this was a conjecture. It's called the 4 color theorem. And the question is, for any planar graph, is it true that, so conjecture was, if G is planar, then is it true that the chromatic number is 4 or less? Okay. And this was an open problem for a long time, and it was only solved by thinking of all possible configurations of points in a planar graph. And I don't know, it's like there are thousands of different graphs that you can have. So people classified all kinds of planar graphs, and after classifying them, they just went one by one and was able to color them by 4 or less. So it was proved that way. Of course, this was like the first example of a mathematical theorem that was proved using a computer, because it was impossible to do it by hand. So people are still not so satisfied with the proof itself, but nobody has been able to rewrite the proof of this without using a computer assist proof. Like, you can't really prove this in, say, 2 or 3 pages. It's impossible. On the other hand, strangely, if you want to say 5 or less for planar graphs, that does have a human readable proof. But when it comes to 4, there isn't any. So that's an interesting thing.